In this session we will, with a bit of commentary at first, some of the differences between LBAs and so these constrained Turing machines, if you like, with finite tape length, and ordinary Turing machines with infinite tape length. So we'll talk a little bit about some of the differences between them, and then we'll get into a new theorem. We'll have a LBA version of E, so the language here, E LBA, we will show that that is undecidable. So that may be a bit of a surprise. So A LBA is decidable, but E, the empty, E LBA is undecidable, different. So interesting. Right? Okay, so well, here I've sort of mentioned it anyway. So if your LBA that you're simulating, if it hasn't halted within that many steps, okay, then that means it has to repeat a sequence of configurations. In other words, it's looping. It has to loop. And that this number comes from the lemma. And if you let it run this many steps, then and it hasn't halted, well, therefore it's looping. It has to loop from what the way I was reasoning in the previous session. Okay, and if it's looping, then it's not accepting. So you want your simulation to reject. All right, now. So that theorem 5.9. 5.9. What is that? Oh, this. Yeah, that this is decidable. Okay. So the fact that A LBA is decidable, but A TM is undecidable. Well, there's an obvious difference there, right? So LBAs and TMs differ in one essential way, and that's this difference between the undecidable and decidable for the so-called acceptance problem. What does that mean? Well, this is me saying this. Explaining what it is. The acceptance problems. So can you find a Turing machine that decides whether a machine M, in this case LBA, will accept a string or not? Remember that's just a variant of the famous halting problem. Let me spell out the halting problem again for you. This famous problem. Can you find a Turing machine, M1, let's say, that will tell you whether some other random Turing machine, M2, and some random string W, will that Turing machine M1, will it be capable of telling you, yes or no, whether the Turing machine M2 will accept the string W? Well, that's the acceptance problem for Turing machines. Well, the acceptance problem here is the only thing you change is instead of TM you have LBA. So the equivalent acceptance problem, if you translate that into the language format that we've been doing consistently, then the language is A suffix LBA, and we just proved from theorem 5.9 that language is decidable, different from ATM, which is undecidable. So interesting. Okay. So for TMs, the normal Turing machine, infinite tape Turing machine, that acceptance problem, this equivalent of this, but for TM here, is undecidable. Right here. Now, interestingly, these machines, these limited machines, bounded, linearly bounded automata, LBAs. There are other problems, in other words, other languages that involve these limited machines, limited Turing machines, that are undecidable. Okay? And one of them is this one, E for empty. Okay? Now we've done this sort of thing several times, but now we're doing it for LBAs, and we're going to show that this language, corresponding to a problem, language problem, equivalent, it's a common theme throughout Sipser's text, is okay, this language where M here is now an LBA, it's not an ordinary Turing machine, and where the language of that machine is the empty set. In other words, this machine, M here, this LBA in other words, accepts no strings, it rejects all of them. Okay? So if you translate this language now into a computational problem, what would it be? Can you find a Turing machine, an ordinary Turing machine? Can you find an ordinary Turing machine that will detect whether any LBA, a given LBA, rejects all strings, effectively, this. Okay? So can you find an ordinary Turing machine that takes as input the description of some LBA, and that Turing machine can tell you whether that LBA will reject all strings. In other words, its language is empty. Okay, that's the computational problem equivalent form of this language. You can translate readily back and forth. Okay. All right. Okay. So now the next essential idea in this session is so we're trying to prove that this language is undecidable. Okay? And first session, previous board also mentioned in passing a bit that the whole point of talking about computation histories is that they can help proving undecidability of languages via using reduction. Okay. Well, now the moment of truth has arrived. Now we're actually going to do that. We're going to use a computation history, right? And we're going to reduce one problem to another, and that reduction will involve using a computation history. Right? So we're starting to bring it all together now. Right, so theorem 5.10, that this empty, the E LBA is undecidable. Okay? So now unfortunately, even though it's all square, we just get started. I mean, the proof. Well, the proof idea. I think it's like a page and a half. So the proof idea is it's a bit over a page, right, of text. So a rather long-winded outline of the proof. So I'm only just starting, so I'll probably have to repeat this on next session or the next board. So you probably will not get an idea. It won't click what the main strategy of the proof is. But I'll start anyway. Okay. All right. So we're trying to show this. Okay, and the main idea, well, one of the main ideas, we're going to use reduction. Okay, so we'll reduce one problem to another, and so another part of the main idea is we're going to reduce from this. So we'll go from this problem to this problem. Okay. Now, if you can reduce, now that's a bit of revision.